As you know, Hilbert-Einstein gravity is not a renormalizable field theory. This is due to the fact that there are too many, an infinite number of diagrams that should be renormalized. So the people some people think of gravity as being an effective field theory, a classical field theory, with a metric, in fact, being small perturbation around the flat metric. There exist also approaches with the metric as being a small perturbation around the ADS or the DS metric. In this approach, I shall consider the true field as being this H mu here, tensor, metric random tensor, which is defined on a space. In this setting, in fact, the theory becomes a theory defined on the Minkowski space, and the dynamics is given by the standard Hilbert-Einstein action, with here J and the inverse of the metric and also the determinant of the metric are in fact functions of these rational function, polynomial functions in this perturbation H mu. This field is also known as the Pauli Fierz field, as we shall see in the sequel. By kappa here, I denoted the Newton, the Newton constant, the gravitational constant, and this section is in fact an formal series in the powers of H mu, with kappa as the perturbative parameter. Also here, this is written the inverse of the metric, the inverse of the metric written in terms of the Pauli Fierz field. The linearization of this action around the flat metric means retaining from this series the terms of order kappa 0 in this gravitational parameter. In the Hilbert-Einstein action is written as in this formula, and with the first term nothing but the Pauli Fierz action. The remaining terms are seen as perturbations of Pauli Fierz theory. So Pauli Fierz in this setting, Pauli Fierz action describes so-called a free graviton, and this is the complete expression of this action is written in this formula. The action P6, the Pauli Fierz action, is also gauging variant, manifestly gauging variant under the linearized version of the diffeomorphisms. In this Lagrangian action possesses this generating set of gauge transformations, which is abelian and of course closes off shell. So at this point we can approach the gravity as a self-interacting gravity, as a self-interacting theory, starting with the free theory written in P6, theory that can be approached by the standard canonical quantization prescriptions. Namely, it can be approached by first at the classical level by the Dirac formalism, which includes the definition of the canonical momenta, definitions that means that in terms of the complete expression of the Lagrangian density, Pauli fields Lagrangian density have the expression written here. And we have to, in order to pass to the first of the formalism, namely to the Hamiltonian formalism, we should perform the Legendre transform of the Lagrangian density with respect to the generalized velocities. So the definitions of the canonical momenta leads to this generalized velocities and also to this primary constraints written in formula P9. The Legendre transform of this calligraphic L is a Hamiltonian, exhibit this Hamiltonian density written in formula P18. And at this level, we should impose the consistency of the primary constraints. It has to be preserved in time, and these consistency conditions reveals the secondary constraints as these relations hold. At this level, all the constraints, the primary and secondary, are abelian. So the consistency of the secondary constraints reduces only to the computation of the Poisson brackets between the Hamiltonian and the secondary constraints. And by direct computation, we get that the consistency of the secondary constraints produces nothing, namely the Dirac algorithm stops at this level. So the Hamiltonian gauge algebra consists in the primary and secondary constraints which are abelian. So these are first-class constraints. They are gauge generators. And also to these relations P12 and this, which completes the Hamiltonian gauge algebra. At this point, the quantization program of the Pauli fields action comes straightforwardly, either by realizing the canonical fields as the field operators, self-adjoint field operators, and isolating the physical space, physical state subspace by the vectors in the Hilbert space that annihilate the constraints. These are the physical states, or by implementing some canonical gauge conditions and identifying the fundamental classical observables, which are then quantized by canonical quantization. To realize the second version of this program of quantization, one imposes these gauge conditions written in formula 13. We observe here that this is the linearized version of the Donder gauge. Okay. So the reduced phase can be given implicitly by these equations. Okay, so we can identify this with these relations. We can identify the fundamental classical observables, namely the fields that parameterize this surface. These classical observables are the transversal components of the spatial part of the Pauli field, and together with the transversal components of the momenta associated with the spatial part of the Pauli field. Of course, this as in the electromagnetic situation and also in general before case, these transversal fields are non-local when they are written in terms of the original fields. The transversal part means that they should satisfy this equation, namely traceless and also this divergenceless. Okay, and it can be shown that by direct computation that this transversal part is written here, where Wj has this expression in terms of the original fields. So not very illuminating. Well, due to the perturbative aspect of the Hilbert-Einstein theorem, it appears naturally the question concerning the most general self-interacting theory that could be constructed starting from a free limit like Pauli field's action. In dice, is it possible to construct more general theory than Hilbert-Einstein action with free limit is Pauli fields? And to attack this problem, we have to address the problem of constructing consistent interactions for a field theory comprising only gauge fields. This means that we are looking, starting with a free theory with the fields phi alpha and dynamics governed by this Lagrangian, by this functional, which is supposed to be invariant under generating gauge of generating set of gauge transformations, if the S and Noether identities hold. The problem is to construct a field theory with maintain the field spectrum phi alpha 0, such that preserve the numbers, the degrees of freedom of the original theory, and reduces to the original theory in the limit lambda goes to 0, where lambda here is a parameter or a set of parameters which plays the role of perturbation parameter for also the coupling constant. At the classical level, the problem constructing of this functional is solved using the deformation theory. In that one deforms the original Lagrangian action into this into this Lagrangian action associated with the interacting theory, and we deform the generating set of gauge transformations for the original theory to generating set of gauge transformations associated with the interacting theory, as in this formula. This means that the Noether identities written in P16 should be fulfilled. To identify the interacting gauge theory means to identify various order in perturbation theory of the Lagrangian action, and also all others in perturbation theory of the gauge generators written in this formula. This means that it should be solved by the tower of equations P17 obtained by projecting this master equation on various powers in the coupling constant. Remember here that in this context of the gauge field theory, Utiyama procedure cannot be used. Remember that Utiyama procedure assumes from the beginning the existence of matter fields with some rigid symmetries and gauges that rigid symmetries via introduction consequent gauge fields. To attack this problem can be the construction of this functional and this generating set of gauge transformations can be attacked in a more economic and mathematical fashion by in the context of the BRC symmetry, either Lagrangian or Hamiltonian. This is due to Marquenot and his school in 1994, who reformulated the problem of constructing consistent interactions of a deformation problem of the BRC symmetry associated with a given field theory. This is due to the fact that the BRC symmetry encodes all the gauge structure on a given field theory. Remember that the BRC symmetry is a rigid symmetry that replaces gauge symmetry and acts in a space that in a large space that comprises among besides the original fields also anti-fields and ghosts. Anti-fields are associated with the equation of motion for the theory, and also the anti-fields with the ghost fields associated with the gauge parameters of the classical theory. In the Lagrangian setting, the BRC symmetry can be canonically realized in a structure named anti-bracket. Anti-bracket is a structure defined on the module of sections in graded bundle generated by fields, anti-fields, and ghosts, and eventually, depending on the nature of the generating set of gauge transformations, the generating set of gauge transformations is reducible. We have to introduce ghosts for ghosts, depend on the level of reducibility of the generating set of gauge transformations. We will have ghosts for ghosts for ghosts, and so on. Okay, the BRC symmetry at the Lagrangian level, it's encoded in this local functional called the solution to the classical master equation. Classical master equation is in fact related with the nilpotency of this differential. Also, the same mechanism can be enforced at the Hamiltonian level, where the theory is specified by the first class Hamiltonian and by the first class constraints, and eventually the reducibility functions. And the object in BRC formalism are the BRC invariant Hamiltonian and the Hamiltonian charge. So as capital S contains all the information on the gauge structure. On here, the charge contains also all the information on the gauge structure, but H3 contains the information concerning the evolution of the system. S here also encodes the evolution. The problem of constructing consistent interactions can be reformulated as a deformation problem of the solution to the classical master equation, namely the solution to the classical master equation associated with A-free theory can be deformed into this solution as bar associated with the interactive theory, such that S bar satisfies this classical master equation, which is nothing but the hypothesis of the default Biarski differential. Okay, as I told, as I previously said, S bar contains all the information on the gauge structure. This means that the physics of anti-Gauss-Napoleon 0 specify the Lagrangian action. The pieces of anti-Gauss number 1 specify the generating set of gauge transformation. The pieces of anti-Gauss number 2, the gauge algebra, and also the reducibility relations, the first order reducibility relations of the generating set of gauge transformations, and so on. So if we construct this S bar, we have all the information on the interaction theory. To solve, to determine this S bar, we project this classical master equation on various orders in the coupling constant, lambda here, and obtain this tower of equations. Among which this equation is verified by assumption, because S is the solution to the classical master equation for the original theory. It is the, let's say, more or less equivalent with this equation, which is satisfied also by assumption, because R alpha, capital A, are gauge generators for the original action S naught. And the second equation in this tower expresses the first order deformation of the solution to the classical master equation, and this equation is equivalent to the fact that the first order deformation is a Biarski cycle with respect to the Biarski differential associated with the free theory. In our case, as the free theory is linear, the Biarski differential reduces to the sum of two differentials, namely Koszul-Tate differential, which enforces homological resolution of the equation of motion, and here is the exterior derivative along the gauge orbit. Somehow, let's say, in a sense, vertical derivative, which is a true differential in the RST complex, and these two differentials anti-commute and are graded in terms of two n degrees, namely anti-Gauss number and respectively pure Gauss number. The overall degree in the Biarski complex is the Gauss number, which is written as the difference between pure Gauss number and anti-Gauss number. So this equation it has been proved by Mark and his school in a seminal paper in 1994, written by him and Glenn Barnish, that this equation always possesses solution. in the end, we always can construct an interacting theory. There are two problems here. The interacting theory could be trivial in the sense that can be obtained via the original theory only via a field reparametrization. So it's a fake theory, fake interactive theory. Or could be a genuine interacting theory. But genuine interacting theory could also be local or non-local from the point of the quantum field theory. It's non-local theory should be removed. So only not there are situations when this equation does not possess local solution, and the locality of these solutions are analyzed with techniques of BRC cohomology concerning these two differentials. There exist general results for linear gauge theories of any order with an arbitrary generating set of gauge transformation with the gauge generator not depending on fields. In the same paper, it has been proved that if this equation possesses solution and this possesses solution, the remaining equations also possess solutions. So the only problem with this equation is the locality that can be investigated for each theory under study. The same situation has been the same problem has been formulated in the Hamiltonian setting. Remember here that at the Hamiltonian level, the BRC symmetry is generated via a canonical action in an extended Poisson bracket that includes among the original space variables also the ghost and anti-ghost, which are paired in this extended Poisson bracket. And the nilpotency of the BRC symmetry is reflected by this equation verified by the BRC generator. And the invariance of the local function that gives the evolution, the time evolution, is given by this equation. So in order to construct an interacting theory, we should, as we also I already mentioned, we should deform the BRC charge as in this relation and the BRC invariant Hamiltonian as in this series. To identify the various contributions to this series, we project these equations on various powers in the coupling constant and obtain these towers. Also here, this equation and this equation are satisfied by assumption, as omega and HB are the BRC charge and BRC invariant Hamiltonian of the free theory, and the remaining equations should be solved. Also here, it has been shown in 2000 by our group in Craiova that this equation always possess solutions. The same problem as above is with locality. The locality also can be tackled. This is nothing but this is equivalent to S acting on omega 1 equals to 0, and this is the Hamiltonian DSP symmetry. And this is also can be decomposed as a sum between the Koszul-Tate differential and the derivative along which orbits. Here, the Koszul-Tate differential enforces the resolution of the function defined on the first class surface. Okay, and the same problems appear with locality. Always this equation possesses solutions, but they are not always local. Applying this both of any of these two methods, previously we used each of these to arrive to these conclusions. We can conclude the following facts. The first fact is that we impose restrictions on the number of derivatives in the interaction vertices. Namely, we allow only at most two space-time derivatives of the field. We get nothing but the Hilbert-Einstein attention with the cosmological constant. Even the cosmological constant wasn't included since the beginning, as we see from this Pauli section. If we relax the number of space-time derivatives, but we maintain the order of the equation, the differential order of the equation of motion, we reproduce Lovelock gravity, the formulation that I talked about yesterday. Applying the same mechanism, it has been proved by Mark and his school no-go results concerning interacting multigraviton theories, namely, contrary to quark field, or let's say lepton content of the standard model, graviton cannot have color. It's only a color of graviton. By applying the same, if there are eventually more than one colors of the graviton, then they do not fill each other. Okay, and the last result, the general result that have been obtained in this approach concerns the interactions between Pauli fields action and matter fields. By matter here, it's this attribute is matter from the point of view of gravity. Any other field, gauge, or true matter. Concerning these interactions, has been reproduced the standard interaction vertices, minimal coupling vertices, but also if we relax the number of derivatives in the interaction vertices, more interesting interaction vertices have been obtained. This is my talk.